Okay, and I'm going to share my Elmo. I was having trouble with this earlier today where it was not focusing. We'll see if I have better luck now. Okay. Much better now than this morning or this afternoon. Much, much better. Okay. So we're going to be drawing some Lewis structures for the following molecules or ions. And what I'm going to do is I'm going to take you through this step by step so that we know what to do. So for A, to draw the Lewis structure, and for all of these, the first step is to count valence electrons. Now, to count valence electrons, if you're in group 1A, you have 1 valence electron. If you're in 2A, you have 2. If you're in 3A, you have 3, and so forth, all the way to 8A, you have 8 valence electrons. So the number of valence electrons for a particular element is going to be determined by its group number, okay? All right. So to count valence electrons for bromine, and this would be called bromine pentafluoride. So there are 7 for each bromine because it's in group 7. There are 7 for each fluorine because it's in group 7, but there's 5 of them. So essentially you're going to have 42 electrons. Okay, second, so that's the first thing you do. Second thing you're going to do is you're going to choose which atom is going to be your central atom. And if you want to know how many bonds an atom makes, if we look at 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A, and we look at lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And this is in the second period. Lithium makes 1, beryllium 2, boron 3 or 4, carbon 4, nitrogen 3 or 4, oxygen 2, 1 or 3, fluorine 1, and neon 0. So the number in parentheses is what it can do. The one outside of parentheses is what it normally does. So if you take a look here, it goes 1, 2, 3, 4, 3, 2, 1, 0. And these are called electron dot symbols for the elements. An electron dot symbols tells you how many valence electrons they have. So here in 3A, boron has 3 valence electrons, so you have 3 dots. Now, when you get to nitrogen, we're pretending that each side of the element has 4 sides. So I have 3 that are unpaired and I have 2 that are paired for my 5 electrons there. Oxygen needs 6, so 2 of them are going to be singles and 4 of them will be part of pairs. And the way to remember how many bonds an atom normally makes for an element, it's the number of singles. 1, 2, 3, 4. These 2 are not singles, they're a pair, but there's 1, 2, 3 singles, so it normally makes 3 bonds. Oxygen, there's 2 singles, it normally makes 2 bonds. Fluorine, there's 1 single, it normally makes 1 bond. Okay. So in period 3, it gets a little better. So when we look at sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. We're looking at 1, 2, 3, 4, 3 or 5, 2 or 4 or 6, 1 or 3 or 5, and 0 for argon. So you see it's the same pattern, 1, 2, 3, 4, 3, 2, 1, 0. But the exceptions here are a little bit different. One of the things you're supposed to notice about the exceptions is that they always go up by 2s, 3, 5, 2, 4, 6, 1, 3, 5. When we get down to the elements below here, like bromine, it's 1, 3, 5, 7. And iodine, it's 1, 3, 5, 7. And for krypton and for xenon, krypton is actually 0. Xenon, I think, is 0, 2, 4. And krypton can be 0, 2, 4 also. Okay, so you kind of want to know how many bonds a element makes. And the reason for that is because in the second step, we want to choose one of these atoms as being the middle atom. And the one you choose as being the middle atom is the one that can make the most number of bonds. So when we're comparing a bromine to a fluorine, fluorine can only make one bond. Bromine can make 1, 3, 5, or 7. Well, gosh darn it, we're going to put bromine in the middle. Okay, so we're continuing on with A. We're going to put bromine in the middle, and we're going to put the fluorines around it, all 5 of them. And what you see is a line between each bromine and fluorine. So this is the second step, or the third step, I should say. We've decided bromine is going to be the central. The third step is, okay, we'll make it the central and put a single bond between it and the other atoms. The single bond is 2 valence electrons. Okay, now the fourth step is to put valence electrons on all of the terminal atoms, not the central, but on the terminal atoms, one at a time, until they have an octet. When you put them on there, you're not putting them on as bonds, you're putting them on as what we call lone pairs. So there's one fluorine, and we put as many lone pairs on that as we need so that we can get 8 electrons around the fluorine. So we have to remember that the line is 2 electrons, and we have 2, 4, 6, 8 electrons on fluorine in octet, and that's what we're shooting for. You'll notice here that I'm doing one fluorine at a time. And that's the way you're supposed to do it. Okay, now when we count electrons, I like to count by 8s. There's 8 around this fluorine, 8 around this fluorine, 8 around this one, 8 around this. So I have 5 of these with 8 around each of them. And so 5 times 8 is 40. Now, if you remember right, we counted out 42 electrons, not 40, 42. So what do you do once you get these octets on all of the terminal atoms? And the answer is you put the rest of them on your bromine, your central atom. Luckily, I'm writing with pen, so the dots come out pretty well. And then 2 on bromine. And this is your Lewis structure for this compound.
I have a question.
Sure.
So the bromine is just going to have, so basically this is based on the fluoride, because the bromide can be anything. It can be the 5, what is it, the 1, 3, 5, or 7.
Here, how many bonds does it have?
Okay.
It has 5, but it also has a lone pair. This does not tell you how many lone pairs you're going to have.
Yeah, so it's just going to be contingent based on off of the formula, right? Off of the
What's going to be contingent on that?
So this is bromide fluoride, right? So that's, so I guess in your choice to place bromide in the center.
Right. So if we look at this chart here, we've got to put one of these in the middle. And we've got 5 fluorines and 1 bromine, right?
Right.
So you might say, well, we got more fluorines. Let's put one of those in the middle. But fluorine can only make a single bond.
Right.
So
Exactly.
can fluorine be in the middle?
Right. Exactly. So because bromine can form more different bonds, it will
Actually,
just mold to whatever
the way we do it
needed.
is that if you have a tie between how many they normally make, choose the one that can make more bonds. Always choose the one that can make more bonds as the middle atom, unless the problem tells you otherwise.
Okay.
Okay, so this is the Lewis structure for this compound right here, BRF5.
So it doesn't matter how many electrons the bromine has around it, right, at the end, because it has a lot.
Yeah, it actually has 12, and it's called a hypervalent atom.
Right. Okay.
Take
Yeah.
a look here. Which are the atoms that can be hypervalent? Well, certainly phosphorus, right? It can have 5 bonds. That's 10
Right.
electrons.
Mm-hmm.
Sulfur can have 6 bonds. That's 12 electrons. Chlorine can have 5. That's 10. And what do all of these atoms have in common that can be hypervalent? And the answer is they're in the 3rd period.
Mm-hmm.
And these can be hypervalent. Where are they? In the 4th period.
Mm-hmm.
And these can be hypervalent. Where are they? In the 5th period. So which are the ones that cannot be hypervalent? That is to say, they can't have more than 8 electrons. Right here, group period 2. And period 1, we skip period 1, but here's hydrogen. How many bonds does it make?
Just one.
Yep. And here's helium. How many bonds does it make? None.
None. Yeah. Mm-hmm.
It's a noble gas. It's unreactive, so it doesn't bond.
Okay.
Okay. So that's how we're going to do this. Let's do another one. Did that sound sufficiently happy? Let's do another one.
Yeah. For 6, what is it? What time is it for 6 p.m.? I think it's sufficient.
Yeah, it's after 6.
Yeah.
Okay, so here's IF3. Iodine is in group 7A. Fluorine is in group 7A. But there's 3 fluorines, so we basically have 28 electrons, right? Now, you'll notice from that periodic table, if they're in the same group, the one that is lower can make more bonds, right?
Yeah.
So here, which one are we going to choose as the central? We're going
The
to put iodine in the middle.
iodine. I always pronounce that wrong.
Or you
I
say
don't like to say
iodine?
it. I don't like to say it because I always pronounce it wrong.
No, most people say iodine.
Yeah, that's what I say.
And I say iodine
Yeah,
because,
you say it's iodine. I know.
because it's chlorine, right?
Yeah,
And
makes
it's
sense.
fluorine, bromine, iodine.
But I pronounce almost every element wrong, which is why I don't like.
Oh, how about carbon?
Oh, well, that one's pretty easy.
There you go. So do you see how this is how we would arrange them?
Yeah,
What's the next step?
to count the electrons.
We already did that.
Oh, I mean, like, or organize them around the.
So the ones on the ends are called a terminal.
Right.
This is like here, this is an airport. This is a hub. And what are these things out here that you go to catch your plane on?
Mm-hmm.
Terminals, right?
Okay.
Okay. So you put lone pairs. So that's a pair. And the reason they're called a lone pair is because they're on one lonely atom. They're not between 2 atoms like these are. They're on one lonely atom, lone pair. So you put lone pairs on the terminals and you put as many as you need so that you get 8 total. That includes the bonding pair. So 2, 4, 6, 8. Are you good?
Yeah.
Okay. So can you see how this fluorine is going to look pretty much the same?
Mm-hmm.
And this one's going to look pretty much the same. Now we want to make sure we don't use more than 28 electrons.
Yeah.
And how many have we used here?
24.
24. So you put the rest on the central atom. Doesn't matter how many there are, you put the rest there.
Mm-hmm. So you just orient them at the bottom, or does it not matter? Well, yeah, you can't because the other ones are being used for the double
Depends on
bonds.
how you drew it in the first place. I mean, if you drew it like this, I'd put them over here. Basically, I'm putting them where I have space for them.
Yeah. Okay. So that's not as important.
No, it becomes important later when we talk about molecular structure or molecular geometry.
Okay.
This is just called a Lewis structure, which
Okay.
tells you how they're connected together, but not how they're arranged spatially.
Mm-hmm.
Okay. All right. So we've got octets all around. Iodine has more than an octet, but notice the iodine has 3 bonds. Iodine normally makes 1 bond, but it can also make 3, 5, or 7. So this is okay.
So the exceptions, we just have to memorize them.
Yep. The exceptions are anything in period 3 or greater can have more than 10 electrons or more than 8 electrons.
Okay.
And in group 2A, there are some that can have less than 8. And in, I should say in period 2. In period 1, none of them has 8. Hydrogen will end up with 2. Helium has 2, and that's it. Okay. So this is the structure for IF3, which is called iodine trifluoride. How about IBr2 minus? Let's take a look at that one. Now this one, you notice there's a charge, right? So for the iodine, there are 7 electrons. For the 2 bromines, there's 7 times 2. And for the charge, you add 1 more electron because it's a valence electron that gives this thing its charge. So even though it's a negative, we're counting electrons here, so that's an extra electron. And here, this ends up being 22 electrons. Are you okay with that?
Yep.
Okay. Now, bromine normally makes 1, but it can also do 3 or 5. Iodine normally makes 1, but it can do 3, 5, or 7. Iodine is lower on the periodic table than bromine, so guess which one goes in the middle?
Iodine.
Iodine. Okay, now what do we do next?
Start placing the electrons around the terminals.
That's right. And how many have we used?
16.
16, and we need to use 22. So 16, 17, 18. Wait, I counted wrong, didn't I? 16,
Yeah, you've placed 20, so
20.
2 more.
22. Now notice here, I didn't put 3 on one side and 3 on the other. Why is that?
Yeah,
And the
because they
answer
have to go together.
they have to go together. They have to
In
go in
pairs.
pairs. The only time you don't put them in pairs is when you have an odd number of electrons. This is not one of the problems, so I'm going to make this E. We don't have an E. Let's look at NO2. Nitrogen is in group 5A. Oxygen is in group 6A. We've got what looks like 12 plus 7, or 12 plus 5, 17 electrons, right?
Mm-hmm.
Nitrogen, its electron dot structure looks like this because it's in 5A. Oxygen, its electron dot symbol looks like this because it's in group 6A. How many bonds does nitrogen normally make? 3, because it's got 3 singles. Oxygen, 2, because it's got 2 singles. So which one do we put in the middle here?
Possibly nitrogen.
Absolutely nitrogen. You put the one that can make the most bonds in the middle. Okay, so now what do we do?
Place the electrons around the terminals.
Right.
Count the electrons, 16.
So we place one more here, right?
Yeah.
Now we want to get an octet there, but we can't. We can't get an octet because we have an odd number of electrons. But we want to get close to an octet. So here's what we do. Do you see how I took this lone pair and basically I put it right there and made it into a double bond? Okay, so that's what I would do. But I could also do this. I could take the lone pair from this oxygen. So this is 1, this is 2, this is 1, this is 2. I could do it either way. And the reason we draw both of these is for this reason here. You see this double bond and you see this single bond? Double bonds are shorter than single bonds because bonds are like rubber bands pulling the atoms together. When you have 2 rubber bands, the atoms get pulled together closer than 1 rubber band. Okay? So if this were correct, this would say that you've got 1 long bond, the single bond, and 1 short bond, the double bond. When we study this molecule, there are not 2 different lengths of the bond. There's only 1 length. And that length is about halfway between a double bond and a single bond in length. So it's kind of like a bond and a half. So the idea of drawing both of these is that this oxygen is oxygen 1, this nitrogen is the atom number 2, this is the 3rd atom, and these are the identical atoms. So we're saying this structure is not correct, this structure is not correct. It's kind of an average of the 2. So look at this oxygen number 1 and this nitrogen number 2. It looks like a single bond, it looks like a double bond. So what is it? It's actually a 1.5 bond. And this one between 2 and 3 is a single bond, double bond. What is it? It's a 1.5 bond. Now, if they're both bond orders of 1.5, that means that they should be identical lengths because they're the same bond order. Single bonds between the same atom are the same length. Double bonds between the same 2 atoms are the same length. And here, if you have a bond and a half between the same 2 atoms, it should be the same length. So this is a bond and a half. This is a bond and a half. They're the same length. So this is an example where you're going to end up with an odd number of electrons. And guess who gets the odd number? The one in the middle, because you deal with that one last. Okay?
Yeah, so is that the most correct form of?
You draw both of them.
Okay.
Okay, so let's look at BRF2 plus. So how many electrons due to the bromine?
7.
Yep. How many due to a fluorine?
7 times 2.
Okay. And how many due to the charge of +1?
An extra 1.
Wouldn't an extra electron make you negatively charged?
Yeah. So you have to
So
remove 1.
we have to remove 1. So that's how we do it.
Okay.
So there's 20 electrons. And mind you, these are valence electrons, not total electrons, just the ones on the outer shell. Okay, so who we're going to put in the middle?
Bromine.
Bromine is the monkey in the middle. Okay, now what are we going to do?
Start placing the electrons around the fluorine.
Right, until we get an octet. And you put them down as lone pairs till you get an octet. So we have octets, and how many electrons have we used?
16.
So how many more do we have?
4.
1, 2, 3, 4.
Mm-hmm.
Now, this is kind of an odd one out because bromine normally makes 1, 3, or 5 bonds, or 1, 3, or 5, and here it's only making 2. But we're not left with any choice because fluorine only makes 1 bond. Now, one of the things I forgot to show you for C, which I'm going to show you for D, is that when you're done here, you have to do this. So what do I have to do up here?
Place brackets.
And
Oh, add the charge.
correct. So when you don't use brackets, it means it's a molecule. It's not an ion. When you use brackets, it means it's an ion. And you always
Right.
put the charge on the outside of the bracket.
Mm-hmm. Okay.
Okay, so those are those molecules and ions. Okay, so that was for those 4. Let's take a look now at number 14. Determine the formal charge on each atom in the following molecules or ions. So here we've got SCO. Now, to be able to determine the formal charge, guess what you have to do first? Get the Lewis structure. So how many electrons for sulfur?
6.
Okay, how many for carbon?
4.
How many for oxygen?
6.
So that's 16, right?
Mm-hmm.
Now, sulfur normally makes how many bonds?
Normally makes 2.
Carbon, how many?
4.
Oxygen, how many?
2.
Okay, so here we have a clear choice because with the normal amount of bonds that they make, carbon normally makes more, so we're putting it in the middle.
Right, okay.
So the only time you go to the numbers in parentheses is when there's a tie. Okay, so like if we had SO2 here instead of SCO, we had SO2. Well, who do you put in the middle when sulfur normally makes 2 and oxygen normally 2? You put sulfur because it can also make 4 or 6. Oxygen can only make 2, 1, or 3. And when you look at the tiebreakers, oxygen's tiebreaker is a 3. Sulfur's tiebreaker is a 6. So you put it in the middle.
Yeah.
Here, since there's no tie, we're just going to put carbon in the middle. Okay, so we're going to put the electrons around oxygen first. And the general rule of thumb is you put the electrons around the more electronegative atom first. The electronegative. So when we say electronegative, it's the atom that likes electrons the most. And the way it works in a group is that the ones at the top have a high electronegativity. The ones at the bottom have a low electronegativity. So oxygen is more electronegative than sulfur. The way it works in a period is that the one on the right has a high electronegativity, one on the left has a low electronegativity. So if we were to compare carbon and oxygen, oxygen's more electronegative because it's more to the right.
Mm-hmm.
Okay, so we put the electrons on the more electronegative terminal atom first.
Mm-hmm.
And now we put the rest here. Now, in this case, we run into a problem that we haven't run into before. We don't have an octet on carbon, but we do need an octet on it. So what are the ways to get an octet on carbon? There are 3 ways of doing it. One way is this way. So can you see that I took a lone pair and made it into a bond, and another lone pair and made it into a bond? So we end up with what's called a triple bond on the left of carbon.
Yep.
Now, if we count electrons around the sulfur, we count its lone pairs and the bonding electrons, 2, 4, 6, 8. So it's got an octet. Carbon, 2, 4, 6, 8. It's got an octet. Oxygen, 2, 4, 6, 8. It's got an octet. Now, these are called resonance structures, and this is like the NO2 one we did before. What's another way we could do this? Well, we could do this. So what I've done here is I've taken a lone pair and made it into a bond from oxygen. Let me see if I got some white out here. Okay. I took a lone pair from sulfur and made it into a double bond. And notice the carbon has 8 electrons around it, 2, 4, 6, 8. Sulfur has 8, 2, 4, 6, 8. Oxygen has 8, 2, 4, 6, 8. So I have octets everywhere here. And guess what the third one looks like?
It's the triple bond from the right side and then the single bond on the left side.
Right. So a triple bond to oxygen.
Mm-hmm.
Okay. Now to get the formal charge, basically your formal charge is the formal charge on an atom based on how many electrons it should have when it's neutral compared to how many we formally assign to it in the structure. Because the idea here is if it normally has 6 electrons when it's neutral, but formally it has 7, it's got an extra electron, so it's a negative charge. If normally it has 6 valence electrons, but it only has 5, then it has 1 less electron than it should have, which means it's going to have a positive charge. So let's take a look at how we formally assign electrons. So I'm going to do it for this one right here. This is how we formally assign the electrons. So you see these 3 bonds? Those 3 bonds are 6 electrons. What do I do with those 6? I give 3 to sulfur and 3 to carbon. Split them down the middle. Fair, fair, right?
Mm-hmm.
This single bond is 2 electrons. What do I do with them? I put 1 on carbon and I put 1 on oxygen. So this is the formal assignment of electrons. Now the valence electrons, sulfur is this, 1, 2, 3, 4, 5, 6. Carbon is 4. Oxygen is 6. So how does this sulfur compare to this sulfur? This has 5 electrons. This has 6 electrons. And we know the charge on this is 0, the charge on this is 0, and the charge on this is 0. Because they're neutral atoms with the correct number of valence electrons. Well, how do you go from 6 valence electrons to 5? How do you change the charge to account for that? In other words, here you have 6 electrons, now you have 5. What happens to your charge when you lose an electron?
It become a cation. I mean,
Yes, so +1. Here you normally have 4 electrons in your neutral, 4 valence electrons. And here this has 4 valence electrons. So what is its formal charge?
um, wait, 1, 2, 3.
It normally has 4, and now
Oh, it
it has
normally has
4.
4, yes. Mm-hmm.
So it has what it should have. So that means its formal charge is going to be 0.
Oh, okay, I see. I get it.
Now this guy normally has 6, and now it's got 7, an extra electron. What is its formal charge?
Yeah, so you're gonna have a negative.
Right. So here I'm going to put +0, negative. Okay, how about this sulfur? How many does it have when it's neutral?
2?
Nope, 6, because it's in
6.
group 6A.
Oh, right, 6, yes.
How many does it have formally according to this structure?
4.
Nope,
Oh, wait, it has 8.
nope, it has 6. Because remember, the formality is we split these.
Oh, that's right.
So it has 6, right?
Right, right.
And it should have 6, so its formal charge is 0.
Okay, okay.
How about this carbon? How many should it have if it were a neutral carbon atom by itself?
4.
4. Now here it's got 8, but they're all bonding electrons. So how
Right.
many of these electrons does carbon get out of these 8?
4?
4. And it
Yeah.
should have 4, right?
Mm-hmm.
So what's its formal charge?
0.
0. This oxygen is in group 6A, so it should have 6 valence electrons. It outright owns these 4. It owns half of these 4, right?
Mm-hmm.
So that's 2. 2 plus 4 is 6.
Mm-hmm. 0.
Formal charge is 0. How about this sulfur here? How many electrons should sulfur have if it were neutral?
6.
Correct. How many does this have formally?
7.
7. So what's its charge when it has an extra electron?
Negative.
That's right. How about this carbon? What's its formal charge?
4.
No, it's formal charge. So I'm just going straight.
Oh, sorry, sorry. I keep getting confused. What do you? Oh, I thought it. Wait, isn't it 4? No, it's not 4.
Normally has 4. Right.
Uh,
How many does it formally have?
oh, you mean there? Okay, there it has. What is it? So that's 1, 2, 3. Wait, that's not 4.
It does
Carbon?
it has 4 electrons, right? And how many does it normally have when it's neutral? So here we have lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine and neon. How many electrons should carbon have if it were just a neutral atom?
I
1A,
thought it was on period 4, so wouldn't it have 4?
group 4.
Oh, I mean group 4, yeah.
So yeah, it has 4. How many does this have formally? Based on
So
our
it's taking one from, so it's a triple bond and it gets half of that, right? So that's 3.
Uh-huh.
And then on the left it has a double bond, so that's 4, isn't it?
That's not a double bond, that's a single, right?
I mean a single bond, yeah. So it gets another one there. So that's 4 in total.
Okay. So what's its formal charge? Not its formal number of electrons. What's its formal charge then?
0.
0. So I'm going to ask you for this oxygen, the very last question. What's its formal charge?
Oh, okay. Sorry. I just kept getting confused with with the terminology.
Yeah.
So if you have, it's supposed to be 6, and then you have 1, 2, 3, 4, 5. So then it would be positive.
That's right. Okay, so these are the 3 resonance structures for this, and these are the formal charges based on the 3 resonance structures. Now, how do we use formal charges? We use them as follows. The best Lewis structures are the ones where the formal charges are all 0. So is there a best one here?
Yeah.
This one, right?
Right.
Now, ones with -1s and +1s are kind of okay. But if you have one that are all zeros, you just say, well, those don't count.
Okay.
So if you can get all zeros, that's the one you go with.
Okay.
Now, if we had to choose between these two, which one would we choose? And the answer is you would choose the one on the left. And the reason is this. You want the negative formal charge on your most electronegative atom. And you see over here, if you have oxygen here, sulfur here, and carbon here, to the right is more electronegative and higher is more electronegative. So oxygen is the most electronegative atom out of these. So if you had to choose between these two, you'd choose the one on the left because you get the negative on oxygen. You don't want to put a positive on oxygen if you can avoid it. Well, we don't have that problem. We're left with that. Why do we like this one the best?
Because it has a 0.
All
Net
formal
charge.
charges are 0. That's the best you can get. That's
Okay.
the best of the best. That's the creme de la creme. That's the, I don't
So
know.
you can have a Lewis structure like that for all of them, or is it in some cases just not possible?
It's not possible sometimes. If we're talking about an ion, you're always going to have a formal charge that's not 0. One of the things that you didn't notice, and I'm going to point out to you though, look at these formal charges here. What do these all add up to? +1, 0, and -1.
Yeah, they add up to 0.
What do these add up to?
0?
It sounds like a question. Are you questioning yourself that 0 + 0 + 0 is 0?
I don't know, because you're asking it, so I'm like, is it
Well, I'm
not
just
0?
asking.
Oh.
You took, this isn't even algebra, it's math. What's the addition of -1, 0, and +1?
Yeah, it's 0.
So when you add up these formal charges, they all add up to 0 regardless, right?
Yeah,
What's the charge on this molecule?
there is none.
0, right?
Mhm.
And if we go back, we're going to see for this formate ion, because it's a -1 charge, there's got to be something that's got a formal charge that's not 0. And all of the formal charges have to add up to -1. So
Yeah, so it's gonna happen regardless of which one you draw.
yeah, so let's take a look at this guy, B. Now, for this formate ion, how are we going to do this? This one, they don't really tell you much about it, so I have to tell you about it. Actually, I guess I don't have to. How many electrons? How many for a hydrogen?
1 plus 4 plus 12. So we'll have 15. No, wait, I'm sorry, 17. And then plus a negative, so it'll be
Plus
an
1.
extra plus 18 in total.
Okay, we add one because to get the negative, you have to add another electron. Remember, these are
Mhm.
electrons. Okay, so we're looking at 18 electrons. Which atom are we going to put in the middle? Hydrogen that makes one bond, carbon that can make four, or oxygen that normally makes two?
Carbon.
Okay, carbon in the middle. I'm going to put hydrogen here and oxygen here and oxygen here. What next?
Start placing the electrons around the hydrogen and the
Well,
oxygen.
hydrogen only gets two. And there they
Oh,
are.
wait, yeah, hydrogen's good. So you can start placing them around the oxygen.
Now I'm going to show you a little drawing of why hydrogen is good. This hydrogen is like that, right? It's got two electrons.
Mm-hmm.
So another way to draw these electrons is like this. You don't have to draw them like a bond, but I like to draw them like a bond. Now, this hydrogen here with its two electrons is thinking, damn, I look just like helium. I look good with these electrons, right?
Right.
And if it looks like helium, it acts like helium. What do we know about the reactivity of helium and the noble gases?
They are not
They are not. So this
reacted.
hydrogen is kind of stable.
Mm-hmm.
You know, it's trying to dress up and be like helium, dress for the job you want. So this guy is dressing up like helium. So that's what makes it stable, and we don't need to add more electrons on it.
Mm-hmm. Mm-hmm.
Okay, so oxygen, on the other hand, looks like that normally, right?
Right.
What does it want to look like? Well, it wants to look like neon. How many electrons does neon have?
8.
So we want to get 8 on that oxygen. You see how this oxygen now has 8?
Mm-hmm.
So what are we going to do for this oxygen here?
We're gonna circle it with electrons.
We're going to add
Oh, it has
electrons
8.
till we get 8, right? How many have we added here so far?
We have 18 already.
Okay, but we don't have an octet on carbon. So what are we going to do? There's 2 ways to fix that.
Move some of the single um,
They're called lone
pairs.
pairs.
Single pairs. Oh, yeah, lone pairs. Yeah.
Do you want to remove the lone pair from the top oxygen or the one on the right?
Mm, I don't know. The one on the top.
Okay, so let's do that. So there we go. Do we have octets everywhere?
Yeah.
Except for hydrogen, which is only supposed to have 2, so we're good, right?
Yeah, I think so.
Now, why did you choose the top oxygen?
Hmm.
Because I asked you to choose one. I said, which oxygen? So you said, oh, I'm
I
going
don't
to choose
think it
the top.
matters.
Now, you know what?
Does it matter?
It doesn't, but it does. What I mean by that is you also have to choose this one. So what would it look like if you had chosen this one instead?
Mm, yeah, it would just be the same, but with the lone
Double bond
pairs
there, right? And
mhm,
notice I
on
take
the other
this so
side.
I can make it look symmetrical. And it would look like that. Now, you put a little arrow between these because both of them are correct.
Hmm.
And the little negative sign, these are called resonance structures. Okay, now let's look at the 2 resonance structures, and I'm going to redraw them to give them a little bit of space. Here's one. And here's the other. So I'm just putting space between them. Whoops, and I made a mistake. So now we're going to assign formal charges to each of these and decide which one's better. So let's go back to the formal charge idea. You look at the atom based on how many electrons it should have to be neutral. You look at the atom in the structure and you ask yourself, how many electrons do we formally assign to it? You compare the two to decide what the charge is on the formal one. So where is hydrogen in your periodic table? What group?
1.
So how many electrons should it have to be a neutral atom?
1.
1, yeah. Where is carbon on your periodic table?
Group 4.
Group 4A. So how many electrons should it have to be a neutral atom?
4.
Where's oxygen on your periodic table?
Group 6.
So how many
A.
electrons should it have to be a neutral atom?
6.
Okay, so we know it's 1, 4, and 6, right?
Mm-hmm.
Okay, here we have 2 electrons. How many do we formally assign to hydrogen?
1.
Okay, so it's got 1. It should have 1 to be neutral. What's its formal charge?
Neutral. 0.
Okay, how about this hydrogen?
It is also 0.
Correct. Now carbon should have 4 electrons to be neutral, right?
Right.
Look at this structure. How many of these electrons that are attached to carbon do we formally assign to it?
4.
So it should have 4. It has 4. What's its formal charge?
0.
Good. How about this carbon?
It's also 0.
Right. And it doesn't matter that you have a double bond to the left versus a double, or to the right versus a double bond above. It just matters how many electrons you formally assign.
Mm-hmm.
Let's look at this oxygen above my finger.
Mm-hmm.
How many electrons did you say I'm sorry, back it up. Based on the periodic table, how many electrons should it have to be neutral?
6.
6. How many do we formally assign to this oxygen?
It has 1, 2, 3, 4, 5, 6. Yeah.
Okay,
So
it
it's
should
neutral.
have 6, and we formally assign 6. So what's its formal charge?
0.
Okay. Now, an interesting thing is that when you add up all the formal charges, they should be the charge on the thing. So what's the formal charge on this have to be?
There has to be a negative.
It has to be -1.
Yeah.
Now let's do it based on what we've been doing.
Yeah.
Here's an oxygen. How many electrons should it have on it if it were just a neutral oxygen atom on your periodic table?
Right. It should be 6. But it has
How many does
7.
it have formally?
7.
So it's got 1 extra one. What happens to its formal charge?
Yeah. It has a negative.
So it works,
1.
right?
Okay.
Now, how about down here? Look at this oxygen above my finger.
Mm-hmm.
How many should it have on the periodic table?
6.
How many does it have here formally?
7. So it would be negative.
So -1. And look at that. Both of these oxygens with 1 bond to it and 6 non-bonding electrons,
Mm-hmm.
they both have the same formal charge.
Mm-hmm.
How about this oxygen?
It's a 0 charge.
And when you add these all up, what do you get? -1.
Mm-hmm.
Okay, so here, when we assess both of these, we ask ourselves, is one better than the other? And the answer is no. Here you've got hydrogens with 1. Here you've got carbons with 0s. Here you've got an oxygen with a 0. Here you've got an oxygen with a 0. Here you've got an oxygen with a -1. Here you've got an oxygen with a -1. They're all equivalent. So no one of them is better than the other, and you accept both of them.
Okay.
Okay?
Mm-hmm.
So that is the formate ion. Let's take a look at the carbonate ion. So how many electrons for a carbon?
4,
Excellent. How many for an oxygen?
6,
And then, of course, there's
and
3 of them.
3.
What do we do about the charge?
We're adding 2 electrons
Why are you adding 2?
because there's a 2, it's a -2 charge.
And
You have to add 2 electrons because it has 2 additional electrons.
because you have a -2 charge, you have to add 2 electrons. That's what I'm looking for. Okay, so what's our total here?
24.
Okay, so we've got 24 electrons. Who is the atom in the middle?
It would be probably carbon.
Because it makes 4 bonds, right?
Yeah.
Okay, which oxygen do you want to do first?
Either.
It doesn't matter. So since I'm left-handed, I start at the one on the left and then go to the right. Okay, we've used all 24,
Okay.
but carbon doesn't have an octet and it really needs one. So what are we going to do?
We can just grab a lone pair from any oxygen.
Actually, we want to do it from all of them, but
Oh.
one at a time. So
Huh.
this will be one of them.
Oh, that's right, because we have yeah, the carbon needs more electrons.
So do you see here? We're going to take 2 from this oxygen, make a double bond. Now carbon has 8. But we have to do it for the others as well. So here, now we're going to take 2 from this oxygen, make a double bond, but leave the other oxygens alone. And now this carbon has 8. So we've done it for the oxygen on the left, and we've done it for the oxygen on the right. What else do we have to do? Or excuse me, we've done it for the one on the left. We've done it for the one above. Now what do we have to do?
The one on the right?
Correct. And when you count electrons, you'll notice that we've used 24 in each case. And in one case, you put the double bond here, one case you put the double bond here, one case you put the double bond here. So let's assign formal charges, shall we? What do you want to do first? How about this? Let's do the formal charge on this oxygen, and I'm going to draw it in here. What's the formal charge equal to?
2, 1, 2, 3, 4, 5, 6, 0.
0. So here, can you see that it doesn't matter whether I put the double bond to the right, above, left, or below? It's 0. So let's do all of these like this because they're all zeros, right? Okay, let's do a oxygen that has a single bond. What's the formal charge?
A -1.
Okay, so here's one with a single bond. Here's one with a single bond. Oh, here's another one with a single bond. Here's one with a single bond. Oh gosh, there's lots of them. How about a carbon with 4 bonds?
It's neutral.
So 0,
0.
0, 0.
So does that mean we can pick either any of those?
No, you pick them all.
You have to draw all 3 of them?
They're all good. They're all good.
So we have to draw each possibility?
Yep. And the reason they're all good is because none of them are correct. And here's what I mean by none of them are correct. Double bonds are shorter than single bonds. And the reason for that is the more electrons you have between two atoms, the better it can pull the two nuclei together, or the closer it can pull them together, right? Because the electrons are attracted to nuclei.
Right.
So if you have more electrons, you pull them in tighter. So if we actually drew this, it would look like this. Short, long, long. If you drew this, it would look like this. Short, long, long. And if you drew this, it would look like this. Short, long, long. And so I'm not trying to show you Lewis structures. I'm just trying to show you the short and the long of it. So I want you to imagine, I want you to stand up and put your legs together. Now, don't turn on your camera because you will be totally embarrassed. Now, are you standing up?
Okay.
Put your legs
I guess.
together and stick your arms
Is
straight.
turning into PE.
Yep. Stick your arms straight out. So what I want you to do is I'm going to redraw these so they look like this instead. Okay, so you see this drawing here at the bottom?
Right.
Your two arms and your legs, right?
Mhm.
So if you're this molecule, what should be shorter? How far your arms stick out or how long your legs are?
Your arms.
Which should be shorter? Remember, more electrons, shorter, right?
Right. Mhm.
Okay, so in this case, if these are your legs should be shorter than your arms. So what I want you to do is I want you to kind of bend your knees and get low to the ground. Are you there?
Yeah.
Okay, that's what this molecule would look like. Now what I want you to do is I want you to become this molecule. So for this molecule, you see to the right, you're going to have a short bond, but the legs are a long bond. So I want you to stand up straight. And to the right, I want you to take your right arm and pull it in like you're a chicken, right? Pull in your right arm. Okay.
Right.
Now I want you to do this one, and I want you to stick your right arm back out straight and pull your left arm in.
Right.
Okay, now I want you to kind of do this with your arms left and right. So you're going back and forth, right? Short, short here, short here, short here. You with me?
Right.
Okay, now I want you to stick them both straight out and go short on the legs.
This is like PE.
Yes, and now I want you to stand up straight and pull one of the arms in. And now what I want you to do is kind of rotate around. No. So
I think I'm good.
So here's the dealio. This molecule doesn't behave that way. It doesn't change all over the place. Here's what really happens. Turns out that the bond length there is a little bit shorter on the arms, not as short as a double bond, not as long as a single. It's a little shorter than a single, but longer than a double. And guess what happens with the legs? Same thing, not as short as a double bond, but not as long as a single. So what I want you to do is I want you to pull your arms in just a skosh and bend your legs just a skosh.
Mm-hmm.
That's what the molecule looks like. All the bond lengths are identical.
Mm-hmm.
So which one of these looks like the bond lengths are identical?
None.
None. So none of them are correct. But here's the deal. We have this thing called bond order. And you can sit down now. I have the feeling you've been sitting the whole time.
No, I tried.
So here's the deal with bond order. If it's something simple, it's simple. Here's what I mean by that. If this were the correct one and the only correct one, this bond order would be called 2. This bond order would be called 1. And this bond order would be called 1. So bond order is the number of bonds between two atoms. So what's the bond order here that I'm pointing at?
1,
That's right. How about here?
1,
How about here?
2,
And how about here?
1,
How about here?
1,
How about here?
2.
Okay, so if it were that simple, it's as easy as 1, 2, 3. Because you could also have a triple bond, which is a bond order of 3. And bond order of 3 is shorter than 2. 2 is shorter than 1.
Right.
Okay, but here's the deal. This is more like a bond order of 1 1/3. More than a 1, less than a 2. This is 1 1/3, and this is 1 1/3. If they're all 1 1/3, the exact same bond order, what does that mean about their bond length? And the answer is, well, they're the same.
Mm-hmm.
So how do we get a 1 1/3 here? And a 1 1/3 here, and a 1 1/3 here? Here's how you do it. Remember I said none of these are correct?
Mm-hmm.
The caveat is that when you look at them all together, they're correct.
Mm-hmm.
So let's get the bond order. What's the bond order here that I'm pointing at?
2.
2. And it's between this oxygen and this carbon. Well, this
Right.
oxygen is this oxygen.
Right.
So what's the bond order between this oxygen and this carbon over here in this structure?
It's probably like 1.5.
No, look
Oh.
at it. It's a 1.
Oh, 1. Yeah. I thought
That's
you
a
were
2.
saying to take the average.
That's a 2. That's a 1, right?
Mm-hmm.
And what's this over here?
Another 1.
Okay, so what's 2 plus 1 plus 1?
4.
Okay, so the bond order here is equal to 4 bonds. But how many structures are we averaging together?
3.
So 4 over 3 is 1 1/3, isn't it?
Mm-hmm.
Okay, let's look at this carbon and this oxygen. What's the bond order here?
1.
How about here?
1.
How about here?
2.
How many bonds total?
4.
How many structures?
3.
4 over 3.
Mm-hmm.
How about above my fingers? What's the bond
Same.
order here?
1, 2, 1.
2 and 1 for a total of
4.
over how many structures?
3.
So all of the bond orders are identical because
Mm-hmm.
while none of these is correct, when you look at them all together, they are correct.
Mm-hmm. Okay.
Now, there is a way to actually kind of meld these together so that you're looking at one, what we call a resonance hybrid. And what you do is you keep your eyes, don't move your eyes left and right in your head, move your head. So look at this one, then this one, then this one, then back and forth, and do it really fast. And if you do it really fast, so fast that your cheeks like jiggle, they'll all come together as one resonance hybrid. You want to give that a shot?
I'm not sure. I might get a headache.
It doesn't work. I'll just play with it. I'm kidding. But I always tell that to every class at some time or other. If you move your head back and forth really fast, they'll kind of.
I mean, hypothetically, it might work, but I just think, I don't know if we could shake our heads fast enough, so I'd rather not try.
Actually, I think what happens if you're looking at one thing and you shake your head enough, it separates into 5.
Yeah.
So I think it's the opposite way around. Okay, so that's your carbonate ion. You would draw all 3. And the formal charges are, as we've shown, 0, -1, 0, and -1. Oh, excuse me. Yeah. And if you look at the formal charges, what's 0, 0, -1, and -1 add up to?
A -2.
And that's the charge on this thing.
Mm-hmm.
Okay, so formic acid. Let's try that one. Now, this one is tricky. They don't tell you about it, but I'm going to tell you. You see this hydrogen here?
Mm-hmm.
It's actually attached to an oxygen. And here's kind of the way we figure it out. When they write these out, do you notice the hydrogens are written separately?
Mm-hmm.
That's kind of a clue that something special going on. So here we write hydrogen to carbon. And then because there's two oxygens, we do this. And we would quickly find out if we put a hydrogen here on the bottom, it would not work. And I'll show you what I mean. So if I do that, we look at the valence electrons. There's 1 plus 4 plus 12 plus 1. And that looks like what? 18?
Mm-hmm.
Okay, so I'm going to put 2, 4, 6. Now I've got 8 on that oxygen. 2, 4, and let's see, I've got 2, 4, 6, 8, 10, 12, 13, 14, 15, 16. I've got 18, right?
Mm-hmm.
So this oxygen doesn't have an octet. How do you get an octet on it?
Mm.
There's no lone pair on carbon that we can turn into a double bond, is there?
Mm-mm.
So we're just SOL. That ain't going to work.
Mm-hmm.
But what if we do this and we think, okay, so maybe those two oxygens are bonded to carbon, but this hydrogen is bonded to an oxygen. Now let's give this one a try. Where do you want to put electrons next?
Around the oxygens.
Which one?
First, the one at the top.
That's right, because it's terminal. This one's inside of the molecule.
Mm-hmm.
So you put them on the terminal one first. Now what do you want to do?
The middle oxygen.
Okay, and so here, I think that's 18.
Mm-hmm.
Do you see around this oxygen there's 8?
Right.
Do you see around this oxygen there's 8?
Mm-hmm.
That's 16,
Mm-hmm.
17, 18. Perfect. Now, the problem is, of course, that we don't have an octet on carbon. So what are the two ways of getting it? So how do we get an octet there?
Mm. You have to take it from oxygen,
Which one do you want to try first?
the top one.
Okay, so then we're going to get this. And when you have resonance structures, you do this little double-headed arrow. Since you did the top one first, we're going to do the one to the right second, okay?
Mm-hmm. Mm-hmm.
And here, do you see how I took them from the bottom?
Mm-hmm.
That doesn't matter. I could have took them from the top,
Right.
okay? It just doesn't matter. Here, carbon has an octet. This oxygen still has an octet. This looks beautiful. Here, this carbon has an octet. This oxygen still has an octet. That looks beautiful. But let's assign formal charges.
Mm-hmm.
How about this hydrogen?
It's 0.
Okay, so that means all of them are zeros because all of them have single bonds, right?
Mm-hmm.
How about this carbon?
It is also a 0.
That's right. And this one's a 0 also because it also has 4 bonds, right?
Mm-hmm.
Look at this oxygen. What's its formal charge?
6.
No, formal charge,
0.
not how
0.
many we assign to it formally. 0. So it's
0.
got 2 bonds, right?
Mm-hmm.
And this has 2 bonds and 2 lone pairs, so that's a 0, right?
Mm-hmm.
And actually, I'm going to write this down here. This is not going to be a 0 because it only has 1 bond. What's the formal charge on this oxygen?
It is negative.
And what is the formal charge on this oxygen?
it is positive.
Okay. And when we add all these formal charges, do they add up to 0?
Yep.
And when we add these all up, do they add up to 0?
Mm-hmm.
You're always a little bit hesitant when we're adding zeros
With
because
the
it adds up to 0.
no.
But it adds up to 0, okay? So what's better, formal charges of 0 or formal charges that aren't 0?
Formal charges of 0.
Okay, so here we get to say, this is correct, dump that. So do you see in this case, we actually could decide which one was better.
Right. Okay.
Okay?
Mm-hmm.
And we could have come up with something different. Here's what I mean. We could have done this. So what are the formal charges here? Well, 0, 0, 0.
Can't really see. Okay.
Oh, I'm sorry. 0 and 0. So what we had drawn before was this. These are the same thing.
Right.
Okay, so what I'm trying to get across here is that, even though it looks like I'm drawing it in a very specific way,
Mm-hmm.
you don't have to, as long as you have the right number of bonds between each atom and the correct number of lone pairs. They all represent the same thing.
Okay.
The one thing I don't want to see you do is something like this. You see all the atoms are backwards? How do you know all these atoms are backwards?
The C?
The C, because hydrogen backwards looks just like a hydrogen, and so does oxygen. But clearly, if you look at this guy in the mirror, it's going to look like that, right?
Mm-hmm.
I wish I had a mirror to show you, but I don't. Okay, so that is the formic acid molecule. So how do you determine the formal charge on each of these atoms? First, you get the Lewis structure.
Mm-hmm.
Then you apply that idea of how many should it have and how many does it formally have and compare them.
Right.
Now, I'm going to give you a couple of formulas for also calculating formal charge. So if you don't want to do the how many should it have if it were neutral and how many does it have formally, you can also do this. So what does FC mean?
Formal charge?
Formal charge. Formal charge is group number minus 1/2 of the bonding electrons and minus all of the non-bonding electrons. Or you could write it as a formal charge is equal to number of valence electrons in the dot symbol, which we know is its group number, right?
Mm-hmm.
And then we could say, instead of 1/2 of the bonding electrons, you could say minus the number of bonds. Because isn't the number of bonds half of the bonding electrons?
Yeah.
And then you can say minus 2 times the number of lone pairs. But we're not going to do that. We're going to put minus all of the singles, right?
Mm-hmm.
And I don't really like that one. I kind of like this one because you can make it look like this. What's GN stand for?
Group number?
What's BE stand for?
Bonding electrons?
And what's NBE stand for?
Non-bonding electrons.
Yeah, I kind of like this one best.
Mm-hmm. Mm-hmm.
But you know what? You just make your formula the way you want. I really think it's more important to do something like this and say, hey, we know that's 0. So this has got to be plus, or excuse me, -1 because it's got an extra one.
Yeah.
So I like to teach it this way. You assign electrons formally by saying any shared ones are formally split evenly because we don't like to treat one atom better than the other.
Mm-hmm.
And then you compare that to what you would expect if it were neutral. And the deal with formal charges is they're not really real. They just allow us to decide what structure is going to be better.
Mm-hmm. Okay.
So we should call them fake formal charges.
Mm-hmm.
All righty, we've probably done enough, haven't we? What time is it?
7:25.
Did you say 10:25?
7:25.
Like, oh my goodness. You can't let me go on that long. And
I have to study anyway, so I'm just.
I was going to say, you know, if I'm getting long-winded, you just say, Tony, enough.
Well, I have to study anyway, so I don't really care.
Okay, so I'm going to leave you with this one.
Mm-hmm.
Simply this. What is the central atom?
The central atom will be the sulfur.
Right, because it can make more bonds.
Mm-hmm.
What's the central atom?
It will also be the sulfur.
Right. So here we're in a tie between sulfur and oxygen because it's a 2 and a 2, right?
Right.
And chlorine's normally a 1.
Mm-hmm.
So what we do next is we compare the two that tied at 2.
Mm-hmm.
And oxygen can make as many as 3, but sulfur can make as many as 6. So you choose sulfur.
Yeah, but does it work when you think about it going down the periodic table?
Yeah, also the same way.
Mm-hmm.
Because they can make more bonds as you go down the periodic table. So how about here? What goes in the middle?
The same sulfur?
Yeah, I'm not sure about this one, how it's going to work out. I don't know that sulfur can bond 4 things. So I'm interested to see how this one works. Which one's going to be in the middle here?
That one's for sure sulfur.
Sulfur again, yeah. And this one's going to be sulfur. So it's sulfur in each case. Now, once you come up with the Lewis structure, how can you check it?
The formal charges.
Well, okay, you check. And once you assign the formal charges, how can you decide if you're correct or not?
If they're 0 or not.
Now I'm going to show you. So I'm going to do a new share. Oh, come on. New share. So here, did you see that one, O2SCl2? So I'm going to type in here, O2SCl2. And I'm going to write Lewis structure. And let's see what we get. And here it is. Oops. We're looking for something with 2 oxygens, 2 chlorines, and 1 sulfur.
Yeah, it's right there to your right. Oh, you passed it. Yeah, to your right.
Yeah, so it's right here. Now, what is deficient with this one? What's deficient with it is that the oxygens don't show all 8 and the chlorines don't show all 8. So what do you suspect is going on with the oxygens? I'll give you a hint. 2 lone pairs.
Right.
2 lone pairs would give it 8, right?
Mm-hmm.
How many lone pairs on the chlorines?
Let's see. So we have 7.
Nope. Remember, for Lewis structures, what are we shooting for usually?
8.
8. So how many lone pairs on chlorine to get 8? We see 1 bond. That's a 2 electrons. How many more do we need on this chlorine here that I'm circling?
7. Wait, I'm kind of confused right now.
Well, for the Lewis structures, we're trying to get 8.
Right, but chlorine has 1 from sulfur.
Right, but remember, for counting the 8 on the atom, we look at all of the electrons around it. How many do you see so far? I see 2.
Right, exactly.
So how many more do we need to put on here to get 8 if we only have 2 so far?
6.
Okay, so how are we going to stick the 6 on there so it doesn't affect some other atom? 2 dots, 2 dots, 2 dots. What do you call 2 dots? You call it a lone pair.
Yeah.
So that thing would look like a chlorine with 6 dots around it.
Right.
The other chlorine would have 6 dots around it.
Right.
The oxygens would have 4 dots around them. And the sulfur, being in period 3, can have more than an octet. And in fact, it's got what, 12? Can sulfur make 6 bonds? Well, if we look at our chart, sulfur can make 2 normally, but also 4 or 6.
Okay.
So, and then if we count up electrons, if each oxygen has 8, that's 16, right? If each chlorine has 8, that's another 16, right? 16 and 16 is 32, right? And that accounts for all the electrons that we would think are on here. How many should this have? Well, 2 oxygens at 6 each is 12. Add in a sulfur at 6, and you have 18. Add in a chlorine at 7, and you've got 25. Add in another chlorine at 7, you got 32, and that's how many you should have.
Okay.
Okay, so there's always a way to check your answer. But sometimes you have to figure out what they're not showing you. And I'm going to go back here one more time and see if I can find one where it shows you everything. Let's see. Images. Wow, there are no images of this one up there. But another one here they put is SO2. And notice when I'm searching for these, I don't do any uppercase. I don't try to do any subscript. I just look at that, SO2 Lewis structure. There you go. Look at this one. They even show you this. And this one's not so hot. You see this one with a single bond and a double bond?
Yeah.
Take a guess as to why this one's not so hot.
So we have the sulfur.
Do you see what I'm circling over here?
Oh, which one are you looking at? Oh, sorry, I was looking at the
Well,
wrong
they're
one.
the same, right? Double bond, single bond, double bond, single bond. These are the same, right?
Yeah.
So why is this one here that I'm circling not so hot? All we have to do is look over here. Now, when on this one, if the formal charge is 0, they don't write anything. So How many zero formal charges do we have? One, right on that oxygen.
Mm-hmm.
And here's a -1 and here's a +1. Guess what the formal charges are on this guy up here on the far upper left?
Let's see. I think it is 0.
They're all zeros. So which one's better?
That one.
Yeah. So here, when they draw this with the formal charges of -1 and +1, it's really kind of silly.
Hmm.
You
I was,
should,
I was just trying to see what the difference is between those two. So they put,
difference is in one of them, you got a double bond to each oxygen.
oh, okay,
In
one
the
of
other
them.
one, you got a
Okay.
double bond to one oxygen and a single bond to one oxygen.
Hmm.
And based on formal charges, the one with 2 double bonds is better.
Right. Mm-hmm.
Now, the one here is the one that you would stop at in high school, the one with the +1 and the -1.
Mm-hmm.
And the reason you'd stop there is because in high school, you focus on getting an octet.
Right.
So the sulfur has an octet in this one that I'm kind of pointing at with my cursor, right? Sulfur has an octet, right?
Mm-hmm. Mm-hmm.
Over here, does this sulfur have an octet on the far left?
No, it has more.
It's got a decet because 10 is a dec, right?
Mm-hmm.
Decane, decade. So it's got a decet. So in high school, you focus on getting the octet and you just stop there and you say, you know what? If they take chemistry in college, they'll learn more. And quite honestly, maybe your high school teacher doesn't know.
No, I don't think I learned anything in high school chemistry.
Maybe I should go there and become the chemistry teacher so that they can learn something. Where was that here in Humboldt?
Oh, no. That's in SoCal.
So
Yeah.
we're from SoCal,
Yeah.
where I was born. All righty. So tune in tomorrow if you want to learn some more about this stuff.
All right. Thank you so much, Tony. That was
You're welcome.
helpful.
Have a good evening.
All right. Have a good evening.
All right. Bye-bye.
Bye.